first one to give a lecture for this series. Yeah, well, that's great. Yeah. Yeah, I'm actually not in Canada right now. I'm in Italy, Rome. So it's 7 p.m. here. It's yeah, nice time of the evening. But anyway, so I'm going to talk about the hydrogeology in Canada. And so when Miguel asked me to choose a topic, I thought about presenting on this topic of groundwater surface water interaction, because the interaction happens in a specific environment, but there are common thread that can be applicable to many different environments. So in this case, I'm using an example from semi-arid regions of Canada. So I'm going to tell you more about the climate of where this study was conducted, but also in the agricultural setting. So here's a map showing where you're based at, Chihuahua. And then, so this green region is called the Northern Prairies. It's a very large region spanning both Canada and United States. It has a common climatic and geomorphologic characteristics. So I am from the province of Alberta, and the city where I work at, Calgary, is located at the western boundary of the prairies, right at the foot of this large mountain range. In Canada, we call it Rocky Mountains. You probably have a different name where you are. So it's part of this mountain system. So we're on the eastern side of the mountains, just like you are in Chihuahua. So the climate has similarity. For example, precipitation in this northern prairies regions ranges from about 300 to 500 millimeter per year, which should be similar to what you are getting in Chihuahua. When I looked it up on Google, it said about 400 to 450, so it's pretty similar. But our potential evaporation, that's the amount of water that can evaporate if there is water available, ranges from about 700 to 800 millimeter per year. I believe in Chihuahua, you get about double the amount, 1,500 millimeter per year. So your climate is much drier and much warmer too, because in northern prairies, in the winter, temperature can drop down to minus 30 degrees. It's very cold as a result, and soil freezes down to about 1 to 1.5 meter. So you have this frozen soil that generates very interesting hydrological processes. And then aside from climate, the one big difference is that this northern prairies was once glaciated. So what that means is there is a big continental ice sheet that came down to the Canada and the United States many, many times during the Pleistocene. And the last glacial maximum was about 18,000 years ago. At that time, there's a big slab of ice covering the northern prairies. So in Calgary, for example, there was about 1.5 kilometers thick slab of ice moving around. And then what it did was it scraped off the rocks. So it pulverized the rocks into different size materials, ranging from clay to large boulders. Because it's a glacial process, it doesn't involve sorting by water. So you get the sediments of mixed size with about 10 to 20% clay content. So this is a glacial deposit left by the last glaciation. And because of the high amount of clay, so this glacial sediment, it's called glacial till, has a low permeability. So in terms of the hydraulic conductivity, this material, which was taken from about 5 to 10 meters below the ground, has a hydraulic conductivity of 10 to minus 9 meter per second. It's not very permeable. So that's one important hydrogeological characteristic of the northern prairies region. And another important characteristic is it's rather flat because it was just driven over by glacier. So in the regional scale, it's flat, but in the local scale, there are a lot of these small depressions. These are, sizing about 100 to a couple hundred meters, maybe several hundred meters in diameter, and then only about 5 to 10 meters deep. These small depressions, there are many of them. And because this is a relatively young topography, it's only been about 7,000 or 8,000 years since this topography was formed. Therefore, there's not there are no well-developed drainage networks. So each of these depressions form this hydrologically closed basin. So that means all the rainfalls and snow melt are just flowing down to the middle of this depression and just form these ponds after snow melt. So it's an agricultural region. So that's a major the industry in northern prairies. So typical crops are barleys or wheat, well, oilseed. It's called canola. So that's a Canadian invention, I suppose, several decades ago. One important thing to remember is this is a dry land agriculture. There's very little irrigation. In some parts they irrigate, but not much. So groundwater is not used for irrigation in northern prairie region of Canada. So they grow what they can grow in a dry land agriculture, such as barley and oilseed. And then another important agricultural product, about 50% of agricultural production is cattle grazing. I believe there are some cattle grazing in Chihuahua state. So Alberta is known for producing very tasty beef. And then with the cattle grazing, there's a production of hay. So these are feed for these cows during the winter months. So that's a very large industry in our region. So the rural communities, farming communities, they don't have surface water supply. So big cities like Calgary, where we live, we use surface water supply. But once you're outside the big urban centers, it's all dependent on groundwater. So they use groundwater for the household water use. So this little house here is using this well for their water supply. And they use groundwater for feeding the livestock, such as cow. So groundwater is important of farming life in the Canadian prairies or the northern prairies region. So here's a bit about climate again. So this chart plots mean monthly precipitation in blue and mean monthly potential evaporation in Calgary. So you see that both precipitation and potential evaporation are high in summer months. And then the growing season that starts from April and ends in September, October. So during the whole growing season, potential evaporation exceeds precipitation. So what that means is the plants, those are grasses and the crops, they use up pretty much all of rainfall during the summer month. So when we have a hydrological excess, so excess of a precipitation over potential evaporation are these winter months. So in winter, the precipitation comes in the form of snow. Therefore, the snow melt is the driver of hydrological processes, both for surface water and for groundwater as well. So here's a picture of snow melt runoff. So runoff in this context refers to the amount of water that flows over land. And this snow melt cannot penetrate into the ground because the soil underneath is rich in clay and also it's frozen. So it's like a concrete slab. So instead of percolating down into the ground, the snow melt runs off to the side and then finds these low spots in the ground. So those are the depressions. So this is aerial photo. It's an infrared photo. So that means the water is shown in a dark color. And this is a ground-based photo. I took this photo on the same day around the same time. So this depression here is this one. So there are numerous depressions that's just holding up snow melt water until the ground underneath the depression thaws, and at that point, the snow melt water can percolate into the ground, and then some of that can recharge groundwater underneath. Yeah, so because of this snow melt runoff, these depressions have ponds with a strong seasonality. So for example, this shows an experimental pond in a study site called Saint Denis in Saskatchewan province. I'll talk more about Saint Denis in a few minutes. But you see that the water level in this pond, pond is actually dry in the late fall and winter, and the water level goes up in the spring and then comes down in summer, goes up in the spring, comes down in summer. So it repeats that every year. So it's a seasonal pond. So this is a picture right after the spring snow melt, and this is a picture when the pond becomes dry in summer. So these ponds are important because they host this aquatic invertebrates. So this is an example called the gammarus. So this is rich in protein and fat. So that provide the foods for this migratory waterfowl, such as ducks. So these ducks, they don't stay in Canada in winter. They go down to South Florida. Some of them go all the way down to Mexico and then come back to Canada in the spring so they can lay eggs and reproduce. So these ducks need the ponds with this rich source of foods. So these ponds forming in the depressions are very important aquatic the ecosystem. So the prairie landscape used to be dotted with so many of depressions and wetlands forming in depressions. But then mechanized agriculture became very popular. So this picture was taken in 1948. So it's an air photo of an area in 1948. So this time people are still using horses and cows for agriculture, but then so they started using tractors. So this wetlands are a nuisance. So they don't want to have too many of these wetlands in their farmland. So they drain them. So the lands are cleaned off this wetlands. So it may be good for agriculture, but it's not so great for the aquatic ecosystem because now the ducks have lost their food source. So they have to find other places for their reproduction. So this is one example. Agriculture can have a strong impact on hydrologic system in the northern prairies. So they were concerned about this destruction of wetlands and then what it does to the regional ecosystem. So they established the experimental area. It's called a national wildlife area. So they allow agriculture in this land, but they don't allow farmers to destroy wetlands. So they can study the behavior of these wetlands, both hydrologically and ecologically under the typical agriculture setting. So that's the Saint Denis National Wildlife Area. So it's located here in the central part of the Northern Prairies region. So in the next few slides, I'll show you the example of water levels in these wetlands. In two wetlands. So they have numbers. So there are more than 100 wetlands in this experimental site. So S109 and S50. So this 109 is a relatively small wetland, and the S50 is a relatively large wetland. So they have different behaviors as I show you in the next slides. So this is the depth of water in 109 and 50. So remember, 50 is a bigger one. So 109 has a seasonal pond. So that means the pond forms in spring and it disappears every summer or fall. So this pattern repeats every year. Whereas at 50, we call it the semi-permanent. So yeah, it has some seasonality and it dries up in some years, but most times it holds water throughout the summer, fall, and winter. So it's a semi-permanent pond. So this graph is chopped off here because I want to show you when I arrived at the scene. So 1993, so I was a young, so I visited this study site. This became the topic of my PhD thesis many, many years ago. Now, so why they want to have a PhD student working on this hydrology of wetlands? The reason is this. So 109 was a seasonal pond. You see, they'd already studied for more than 20 years. So mostly thinking about the ducks and other animals. But, you got the seasonal pond and it's got, particular ecological function. And then S50, so this is semi-permanent. So it has always water, so it's good for ducks. The seasonal pond has its function. So you have to have both seasonal pond and semi-permanent pond in the same landscape. Now, this semi-permanent pond became seasonal over the past 5 years when I arrived at the scene. So all of a sudden, the hydrological behavior of this pond is changing, shifting from semi-permanent to seasonal. So that seems to be a big problem for the healthy ecosystem for the ducks. Now, a few years back, there was the very first report of IPCC, Intergovernmental Panel on Climate Change. So the scientists started thinking about climate change back then. So the way how biologists were thinking about is, well, there is this climate change, it's coming up, and then this, the seasonality of ponds are changing. Maybe this is related to climate change. We got to study this. So that's how I was brought in to study the linkage between hydrology and ecology of this prairie wetlands. And then it's 30 years later, this is what happened. So the water in this 50 came back and went down a bit. Well, came back a much bigger time. So now this seasonal pond became permanent. So you see that there is a shift in the hydrologic regime of this wetlands from time to time. So the one take-home point is, one key point of this lecture is that for understanding hydrology and ecology of systems like this, the wetlands in semi-arid regions, such as northern prairies and Chihuahua, you got to have this long-term view. Maybe 10 years is not enough. You have to have this long-term view because the climate, or I would say weather, has this pattern, okay? So it turns out that when they were monitoring these ponds in the early stage, from 60s to 90s, they're in the period where the dry and wet period kind of repeated every five or so years. And then there came a time when things got very dry, okay, so both seasonal and semi-permanent pond became much drier. And then there was a wet period. And then there's a big wet period, which lasted for about 10 years. So water levels went up. And then now we're in the middle of severe drought. So the water levels are coming down. So there is a prediction that this severe drought is going to last for a few years. And then this will go back to how it was in 60s and 70s. So this is just a water level, but everything else changes with this, what we call the interdecadal fluctuation in the weather or meteorology. So the one thing, we cannot confuse this with is a climatic variability, okay? So climate, by definition, is a long-term average condition of meteorology, usually about 30 years. So we can talk about climate of this 30 years, climate of this 30 years, but we cannot talk about climate of last year and 2 years ago. So this fluctuation is just, inherent in the climate we have in semi-arid regions of North America. Now, so what I did as a PhD student was to look at the water balance of this wetlands. We call it the prairie wetlands because these are wetlands in the northern prairies. So it's a closed system, so it's relatively easy to understand. So you have this snow drift, so the snow is drifting in from surrounding farmland into this depression. And also there's a snow melt runoff over the frozen ground. And then there is precipitation in summer, both on the upland and the wetland, and evapotranspiration loss. And sometimes when you have a lot of runoff, there's a spillover of water across the hump into the next depression. And then there's this invisible groundwater exchange. So that turns out it has an important role in the water balance of prairie wetlands. So after studying this for several years, we figured out, okay, so the hydrology of prairie wetlands can be characterized by a triangle. So there is a rise of water level in spring with the snow melt, and there's a gradual recession in summer. And then the size of the spring rise and the angle of summer recession defines or determines the length of this base of the triangle. So this is a time axis. So the base of the triangle indicates the duration of pond, whether that's 2 months or 5 months or 12 months. Or we call it the prominence of the pond. So this is very important for ecologists because it really determines what kind of character this pond has as the habitat for the aquatic species, such as the invertebrates and ducks. So this size of spring rise is important, and then it actually is strongly controlled by the snow drift and the snow melt runoff. So this spring rise is controlled by the input of water from upland. So we need to understand the processes on the upland. So this is what happens on the upland. So we have a crop rotation. So some year we grow wheat, another year oilseed, and some other year we just put the ground to rest, no crop. That's called a summer fallow. So the farmers in this case, cultivate the land, but just keep the wetland from destruction, which is good. But they cultivate to the very edge of the wetland. So that means there is no place for the ducks to hide from predators. Well, ducks can fly, but then these guys, ducklings, when they hatch, they cannot fly. So they need this dense cover of plants to protect from predators. So the wildlife ecologists thought that, well, we need to have some dense nesting cover for these ducklings. So they decided to talk to the farmers. Okay, well, let's just convert some of the cultivated field from wheat or barley to just permanent grass cover. So they use a European grass species, not the native grass, but it's a grass anyways, to put the dense nesting cover for the preservation of wildlife. So they put the cover in the catchment of several wetlands. So here I'm showing a pair of wetlands, 130 and 109. So they had a similar pattern of hydrology until they put the catchment of these wetlands to the grass cover. So 109 always had a cultivation and a crop growth, and that they kept the crop on 109, but then 130, they switched from cultivation to permanent grass. So nothing happened hydrologically over the next 5 years. And then in the meantime, biologists are looking at the success of hatching and of ducklings and protection from wildlife. And it was successful. So putting the dense nesting cover was a good thing for ducks. But then this has happened after that. So after about 5 or so years, hydrological behavior of these two wetlands completely changed. There was a dry period in the early 90s. So the 130, there's no more pond. No more ponds, meaning there's no runoff from the catchment. So this grassing of the catchment basically stopped the production of runoff. There was no more pond. Whereas this catchment was cultivated, so there continued to be runoff, so there are ponds. So this is another take-home point. So well-intended ecological intervention can completely fail unless they consider hydrology as part of the intervention. So they knew what's going to happen to ducklings, but they did not really think about hydrology when they're putting this field to grass. So we wanted to understand what happened. So we started looking at hydrological processes. So there are a couple of things that were responsible for the stoppage of runoff. One was the snow drift. So the snow drift was reduced because grasses were now growing in the catchment of 130. So before the grassing, snow was blowing into the depression, but that stopped. But another thing that was more important was the changing infiltration characteristics. So here is one of my first students when I started in Calgary 30 or so years ago. So measuring the infiltration capacity of this soil in the middle of the field. So remember, this soil has some heavy clay content. So the infiltration capacity is not very high unless there are well-developed network of macropores. So these are the cracks and root holes on the holes made by animals such as earthworms, okay? So that turns out to be the key. But anyway, so this is a photo of experiment. So we did this infiltration experiment in the summer, and we left this ring, and then we did it the same thing in winter when the soil was frozen. So these are the results. So it's a busy table, but it shows a comparison between grassed land and cultivated land. So this is the infiltration capacity of the topsoil for unfrozen condition. So grass had a 300 millimeter per hour, so very high. The cultivated field is still high, 23 millimeter per hour, sufficiently high, but smaller than grass, okay? So in the summer, there's not much runoff because this is high enough infiltration capacity, but in winter, when the ground is frozen, grassed soil still has high enough infiltration capacity. So the snowmelt can infiltrate in grassed field, but not in cultivated field because it's so low. So cultivated field generates a lot more runoff than the grassed field when the soil is frozen. So that was the primary reason why the runoff generation stopped in the grassed catchment as a result of intervention. And then difference again is due to the soil macropores. So in the cultivated field, they cultivate the land every year. So that process destroys all macropores. So they reduce infiltration capacity, particularly under the unfrozen condition. In grassland, that does not happen. So the macropores keep developing for years and decades, so allowing high infiltration capacity. So as I said, so this triangle is important because it determines the duration of the pond or the permanence of the pond. And then this part, the recession, summer recession of water level, turns out it is strongly controlled by the groundwater exchange. In this case, the groundwater loss, infiltration of pond water to recharge groundwater. So I'll just show you an example of this groundwater recharge process under these ponds. So here is an example of an experiment we did in Saint-Denis site. So this is a very little pond in the middle of the cultivated field, but we put a lot of sensors and piezometers to monitor the groundwater levels. So in the next graph, I'll show you the water level recorded in this pond as well as the temperature of soil underneath the middle of this pond. Oh, by the way, so the northern prairie regions have this high density of depression, many depression. There's one here, there's another one, another one. So typically about 10 to 100 depressions over 1 square kilometers. Each is small, but collectively they can have a large hydrological impact. So this is the water level in that pond. I showed you the picture. So it went up with the snow melt and it stayed relatively stable, and all of a sudden it started to decline rapidly around this time, early April. And then this is the soil temperature. Okay, so here, vertical axis is the depth, 0 to 1 meter. And the horizontal axis is the time. And then color indicates temperature. So the blue and the purple are below 0, meaning that the soil is frozen when this color is 0. So this 0 degree contour is called a 0 degree isotherm. So indicating that the soil starts thawing from the top around March 20th. And the thawing penetrates deeper and deeper. And also the soil starts to thaw from the bottom, because this is not a permafrost, it's just seasonal frost. And then two thawing fronts meet around that time. And then there's no more frozen soil. So the water has no barrier. Now it can percolate down to recharge groundwater. So that's when this steep decline in the water level happens in the pond. And then this is the piezometer water level recorded in the middle of the pond. This piezometer was dry in the beginning, but now with the recharge, water table comes up to near the surface. And the same thing, similar thing happens outside the pond as well. So this documents what we call depression-focused groundwater recharge. This happens in millions of these depressions all over the northern prairies regions every spring. So it's an important source of groundwater recharge in this semi-arid region. So here's a schematic showing the importance of depression-focused recharge. So as I said, we only get about 300 to 500 millimeter of precipitation. And the potential evaporation is much higher, 700 to 800 millimeter per year. And this happens during the growing season when we have much of the precipitation. Therefore, the actual evaporation is close to precipitation on uplands. Okay, so the plants take up as much water as available, so there's no groundwater recharge on uplands. On the other hand, in depression, there is snowmelt runoff that brings additional water input. So this actually increases the amount of water available, and that overcomes the evapotranspiration demand. So there's an excess, a little bit of excess, not too much, maybe 10 to 100 millimeter per year. So there is a recharge under the depression. But depression occupies small area, about 5 to 10%. So if you average out over the landscape scale, the recharge is about 1 to 10 millimeter per year. But this is enough to sustain the groundwater use in the region. So another take-home point here is that when you have a dry climate, such as northern prairie regions, maybe so in Chihuahua, we know from studies in Texas and Oklahoma in the United States, this mode of recharge is very common in those states in the US because they have a dry climate. So the recharge does not happen uniformly. It only happens in special places where the input of water is focused. So in this case, depression-focused groundwater recharge. So we wanted to model this depression-focused recharge so we can understand it better, and we can make some predictions with land use change and climate change. So we looked at the existing soil-water balance model. So this is the model used by the agricultural scientists. So basically split the soil into different layers. So there's a water input and output. So we do accounting of the moisture balance in each layer. So in Alberta, the province we live in, we use a model called VSMB, Versatile Soil Moisture Budget Model. So our government uses this model to forecast the soil moisture during the growing season. This is from last year. So the color indicates the amount of soil moisture. The green is higher moisture, the red is lower moisture. So farmers can look at this map and then decide what crops they want to grow. So we thought we can use this model and modify it to simulate the depression-focused groundwater recharge. So here is that VSMB model set up for upland. And then we have another VSMB model set up for the depression. So it's the two models coupled together and coupled by the snowmelt runoff from the upland to the depression. Okay. And then, so depression occupies a relatively small area within the catchment. So upland here and then depression in the middle. So this model calculates the water balance for upland and depression separately, and then look at the recharge from both upland, which is usually 0, and depression, and then calculate the landscape average recharge. So it turns out that the size and abundance of depression is a critical factor for this depression-focused recharge. So we set up this model for a watershed just north of Calgary. So my university will be located somewhere here. It's a watershed about 250 square kilometers. There's so many depressions. You can kind of see the dots on this map. These are delineated from satellite, the air photos like this. So we look at this one here. So they got about 50 or so depressions and wetlands forming in depressions. So we delineate the catchment using this polygon method, and then determined area of the catchment and area of depression. Okay, and then we estimated the depression-focused recharge averaged over this entire catchment. For the meteorological data for 2006 to 2011. And then we simulated the recharge for different ratio of depression area to catchment area. The base case was using the actual meteorological data for the present climate. And then we get the average recharge for the regional scale of 6 millimeter per year. So there are some catchment that has higher recharge, but many of them have a low recharge. So the average is 6 millimeter. And we increase the precipitation to about 20% to look at the effects of increase in precipitation. As we expected, we get higher recharge. But the important thing is that there seems to be the optimal ratio of depression to catchment. So if the ratio is too small, there's too much focusing of a runoff water. So this depression basically simply cannot hold water, just overflows. So there is a little recharge. But if the depression is too large, there is not too much of focusing. So there's not enough of water input in the depression to overcome evapotranspiration demand. So this ratio of depression to catchment is important. And this is the example showing the regional scale simulation over the entire prairie region in our province. So you get a average recharge value less than 5 millimeter in the drier southern part of the province to 25 to 30 millimeter per year in wetter northern part. Okay, so in the last 5 or 10 minutes, I'm going to spend a bit of time explaining why we need to understand the recharge processes or recharge values and its response to climate change. Okay, so I proclaim that the recharge is important. Actually, sometimes it's a key to understand the sustainability of groundwater use. And behind that is the water balance. Okay, so let's look at this typical watershed. Okay, so here is a small stream, and the water table connects upland to the stream. And then there will be a recharge on the upland. And then some of that becomes a discharge, feeding a stream, and also the riparian zone where we have dense vegetation growth. That's important for wildlife because a lot of birds and animals use this riparian zone as a corridor. And of course, stream is important for fish. Oops. And then we might have some farmers pumping water from the watershed. And then you look at the balance between input and output by discharge and pumping, that gives a storage change. So when you have more input than output, you have a storage increase. And if you have more output, a storage decrease. In the case of groundwater storage, that shows up as a water level change. Groundwater level goes up or down depending on the storage change. So over long term, when you have a balanced system, so recharge minus pumping is equal to discharge. So there is a long-term dynamic equilibrium sustaining this discharge, sufficient amount for the riparian vegetation and stream and aquatic creatures in stream. So that's a long-term balance. Now, if you start over pumping from the watershed, from some aquifers, and then that can cause the large drawdown of water level. So this water level is going to go down. And also, when you allow this to happen, and then next long-term balance might be reached. In that case, because there's more pumping, the recharge amount has not changed. So discharge has to decrease, maybe decrease to 0. So that will dry up the streams or springs feeding the streams. So we need to avoid this kind of things if we want to have a sustainable groundwater management. So therefore, understanding recharge is the key for the sustainability. So look at groundwater use in the region around Calgary. So we have traditional users. These are farmers. So these are generation of farmers who have been using this water well as their lifeline, source of water supply. And then some farmers, they don't have their sons or daughters wanting to farm anymore, so they sell their land to a land developer. So they develop the land and build more houses. So all these houses still don't have access to the urban water supply. So in this case, there are 50 or so houses, all new houses. They all have wells. So all of a sudden, increase in water use. And then there is industrial activities. The infamous one is what we call a fracking. Hydrofracking to extract more oil and gas. Alberta is the capital of oil production in Canada. So there's lots of this going on, and this requires a lot of water. And then aquifers, they use some like this. So we have this clay-rich glacial till. So this is a glacial deposit. So this is not an aquifer. It's hydraulic conductivity is too low, but sometimes we have layers or lenses of sand and gravel embedded in clay till. So that can be a good aquifer. And maybe sometimes the river has this alluvial sediments that can be an aquifer. And then sometimes we have this bedrock valley, and that's filled with sand and gravels. So this is another example of aquifer. And then we have this fractured sandstone. So that's the main aquifer actually around Calgary. A lot of farmers are pumping water from this fractured sandstone aquifer. So to sustainably manage groundwater, we need to monitor the groundwater levels. But our government doesn't have too many wells for monitoring. So this area shows 70,000 square kilometers. It's quite a large area, but there's only 27 wells monitored by the government. So it's one well per 2,600 square kilometers. So there's not enough density for effective monitoring. And a lot of these wells are set up for specific purpose by oil companies and other companies. They were donated to Alberta government for monitoring wells, but they're not really appropriate for the baseline monitoring of regional aquifers. So what to do? We need monitoring wells, more wells, but they cost you a lot of money to drill a well. So here is an area we call a Rocky View County. It's a rural municipality around Calgary. So I started talking to farmers around Calgary about monitoring their own wells. But look, you guys use water for your lifeline, water supply. You want to maintain, healthy aquifers. So what you got to do? You got to monitor your own wells. So I talked to the farmers and I gave them this water level monitoring devices. So now we got about 30 or so farmers monitoring their own wells, and then they send me the data every month or every couple of weeks, and then I'll just enter them into this web-based database. So now we can all monitor the water level real time almost. As soon as they put the data up, we can look at the water level. So it's an example of low cost groundwater monitoring network using citizen science approach. So I'll show you an example of two wells, well 20 and well 39. It's monitored by a farmer named Howard. This one's monitored by Dave. These two farmers have been sending me data for many, many years. So with this manually measure the water level, we can track the long-term behavior of water levels in these fractured sandstone aquifers. So you see that there is a recharge event in spring due to that depression-focused recharge, but there are years with no recharge. So these are the years we didn't have a much snow melt. So the water level kept going down, and then there are a couple of years of good recharge. Now we're in the drought phase, so the water is not recharged. And then there's this creek, West Nose Creek. So this is a creek draining the watershed of this farmlands. So the base flow actually has this interdecadal fluctuation. So if you look at the years where the base flow of the creek was rising up, so that corresponds with the years of recharge. And the years the creek flow base flow was going down. So those are the years with no recharge. And we can plot the one of the monitoring well data. So you see that there's a strong correlation between creek base flow and aquifer water level. So this is an example of how useful this citizen science approach can be for the monitoring of the condition of aquifers and also the condition of the creek and aquatic ecosystem. Oh, sorry. So overall, the long-term average, 16 millimeter per year, is the discharge in the creek. So this is roughly equal to the amount of natural recharge. So this is a balanced system, despite this up and down due to the variability in the weather. So this creek is fed by the large spring. And then it looks like this during the base flow period. But believe it or not, there are some trout in this creek. So it's the biologist who caught the trout from the creek. So, so active participation of a community volunteer is important for making sure we have a sustainable groundwater use and a healthy ecosystem. And the universities have a role to play because we can train these people or we can educate these people about what we can do. So to sum up, the hydrology of Canadian prairies, which is dry and cold region, is controlled by snow and frozen soil, and depression-rich landscape left by glaciers, and then agricultural land management. So long-term monitoring is essential for understanding the hydrology of the semi-arid regions, such as northern prairies. And working with local governments and citizen groups useful because we can mobilize our scientific knowledge and then use that for something good for the society. With that, I will just unshare my presentation and I'll give the mic back to you, Miguel. Okay, let's see.
Thank you, Professor. We have some time. We have about 5 minutes for Q&A. We have a little bit of time for questions and answers. If someone wants to ask anything, you can do. Also, you can write in the chat. Si alguien quiere hacer alguna pregunta, yo puedo hacer la traducción sin problema. I'm going to read the questions that we have in the chat. We have some messages from students. Congratulations for the webinar. This was very interesting. Can you talk a little bit more about plants that consume a lot of water? In Chihuahua, we have alfalfa and pecan trees that use a lot of groundwater.
Okay. Yeah, so you mentioned alfalfa. groundwater. So, do you mean that alfalfa is actually using groundwater from the water table, or is that irrigated?
I think that the question means that those plants consume a lot of groundwater.
Yeah, that is true. So alfalfa can have roots reaching down to 3-4 meters. So if you have a shallow water table, they can consume groundwater. But in the Canadian prairies, the water table is typically much lower than that. Maybe 4 or 5 meters is common. So it's rare that either crops or the perennial species, such as alfalfa, can tap groundwater directly. But what does use groundwater are the phreatophytes. So these are willows and other plants that can actually have a deep roots and tap into groundwater. But phreatophytes typically occur in the riparian zone or around the wetlands, and they do use groundwater, but we don't usually see them as a harm to the ecosystem. We actually see willow and other phreatophytes as an integral part of the ecosystem.
Irma Meneses, do you want to say something? Do you want to participate?
Sí,
Uh,
gracias. Lo voy a decir en español porque no me animo en inglés. ¿Ok?
okay, you can do it. Adelante.
Ok. Bueno, también lo escribí. Nosotros nos enfrentamos a varios problemas aquí en las comunidades en la Sierra Tarahumara. San Juanito está por encima de los 2.400 metros sobre el nivel del mar. Aparte de los fuertes vientos, de hecho estuvimos en Saskatchewan y allá me dijeron que las abejas no se enfrentaban al problema del frío, porque en Canadá pues hace más frío que aquí, ¿no? Y me dijeron que nuestro grave problema eran los vientos. Nuestro tiempo para poder sembrar cereales y todo es muy corto, porque ahorita todavía nosotros aquí en la sierra estamos con temperaturas muy bajas. De repente un día hace calor y al día siguiente baja muchísimo la temperatura, entonces estos cambios pues no nos ayudan, ¿no? Queremos hacer la prueba con la besa de invierno, pero bueno, también nos gustaría qué recomendación nos da Masaki.
She's saying we face problems of altitude and wind in the Sierra of Chihuahua since we are above uh, 2000, 2000 meters above sea level. We want to do the test with winter vetch than other cereals because our time to harvest is very short. Uh, do you want to say something about it, Professor Hayashi?
Okay, so what's the question again? So you have a harsh winter climate, and
I think that the main problem that they have is they have problems with related to altitude and wind, and they want to change to another cereals in the Sierra of Chihuahua because the time to harvest that they have is very short.
yeah, so I don't know. That's probably the question for the agronomists. But in Canada, yes, the winter is very harsh, but we have a long growing season. I think from June until August, we only have 3 months of growing season. But the sun is very intense, and then weather is warm. So the wheat and oilseeds and other crops seem to have good harvest. Usually the water is a problem. When you have a drought, the crops fail. Yeah, so I don't know what kind of crops can grow in such a low temperature environment.
It's kind of tricky, right?
Yeah.
Uh, well, we also have some other questions over here. We're almost done. I think this is going to be the last question. Has agricultural changed recharge process in Calgary?
Yes, we don't really have concrete evidence, but agricultural practices did change a few things. For example, in 80s and 90s, it was common to actually till the land. So that they went in with the tractors and then just till the land every year. But now the farmers have switched to zero-till agriculture, not for groundwater, for just preserving soil and all those. So that tend to promote infiltration. So that's one change. And then also now they have a continuous cropping. That means they don't have a year where they put the field to rest. So that changes the snow distribution. So all those things are somewhat, changing hydrologic processes. And then I suspect that has effects on the groundwater process too. But we haven't really seen the effects yet.
Okay. Well, with this, we are going to finish this first webinar for this semester. Professor Hayashi, thanks again. I'll send your recognition certificate by email. With this, we conclude this first conference. Again, we thank everyone for attending. So, well, gracias a todos, and see you next time.
Muchas gracias.
Hasta luego, un abrazo, bye.